Here's a calculator question that deals with kind of a particle motion type question, but actually we're looking at a train travel. So we're looking at distance travel, we're looking at velocity, acceleration, and I like this problem because it has part of it be in relationship to an equation that's given, and part of it that's given in relationship to a table. So it forces you to do two different kind of techniques in one problem. Although you'll see as when you go through this problem, it's actually kind of short. You don't really spend the length of time on this question that maybe you spend on some others. So what we have is a train traveling along a track. In velocity is given in miles per hour for the first half of the trip by an equation, v of t negative t squared plus 20t plus 25. That's for the first 5 hours. And during the second half of the trip, instead of presenting with an equation, they present the table where they give you the time from 5 to 10 hours and then the velocity that goes with those times. And they do have one piece of unknown, so an idea of another generic type problem where they have a k value that they don't tell you the velocity, and that'll come into play at the end of this problem. So part A wants to know how far did the train travel in the first half of the trip. The idea is that we are going to integrate to accumulate. If we integrate velocity, we will get distance traveled. Now the first thing I did do with this question is I immediately graphed my velocity because I'm allowed to use a calculator and I like to have it stored in as y equals as well. So I went to my calculator, I got rid of whatever is in there, and I typed in my equation, negative 5x squared plus 20x plus 25. I did change my window because I'm only going for looking at the 10. Well, for this equation, I'm only looking for the first 5, so from 0 to 5. And then if you want to change your minimum, I went to 0, and you could leave it at 10 or you can make it higher. I'm going to look at graph right now. And what you'll notice is actually the graph is so high that you don't even see it. But the one thing that should stick out is you realize that the train's not changing directions. And that kind of is implied with the idea that it moves along a straight track, that it's not going backwards. But it is nice to have that visual and realize that when I integrate, I don't have to worry about a direction change. So for part A, couple ways to do this, couple ways to write. One thing that you could write is just the integral from 0 to 5 of v of t. If you're unsure if it has a direction change and you just want to be safe, you could also go from 0 to 5 and do the absolute value of v of t. That'll kind of take into a direction change if there was one, and since there isn't one, it will not impact anything whatsoever. And then to that point, you're going to your calculator. We don't want to integrate it by hand, even though we could, but it would take some time and we might make a mistake. So I'm going to go to my calculator. Now that I've already set up my integral, I'm going to get out of this screen. I'm going to go to Math 9 to get my definite integral. I'm going from 0 to 5. My velocity equation has already been typed into my y1, so if I go to the vars button, VARS, to y variables, and hit enter one more time, it'll put it there. If you haven't typed it there, you could just type it in as is. And we find out that we have traveled 166.6 repeating miles. So we can either write our answer, they would accept 166.666 miles. They would accept 166.667 miles. They would also accept, if you wrote it in a fraction form, it would be 500 thirds miles. Now you notice in the problem they did say include unit of measure, so it is important that you are putting that it is miles. That is the total distance that has been traveled. So for this problem, you want to make sure you write down the definite integral that you are evaluating. Use your calculator rather than integrate by hand to get the actual number of miles. Part B wanted to know the acceleration at 3 hours. So a couple things you could do. You could do this by hand. You could also do it with the calculator, and I'm going to show you both. If you want to do it by hand, you would get your acceleration is the derivative of velocity. So you could write that down just so the grader knows what you're doing. Acceleration is the derivative of velocity. So if I take the derivative of velocity, I get negative 10t plus 20. I wanted to know the acceleration at time 3. So I'm going to put 3 in, negative 10 times 3 plus 20, which is negative 30 plus 20, which is negative 10. My unit for this is acceleration, so this is going to be miles per hour squared. You could also write, and I've seen the AP write it, miles per hour per hour. That is also completely acceptable, and sometimes the way that they write it. If you want your calculator to do this for you and you don't want to derive it by hand, then you at least want to write this statement, so that you realize what you're actually doing. Then we're going to my calculator. We want to see what happens when we take the derivative of velocity and plug 3 in. If you go to your calculator and we go to Math 8 this time, we are going to put in that same function, so I can use that same variables button and pull it back up. And we want to plug in 3. and we get negative 10. So definitely a way to do it with or without the technology. If you use the technology, make sure you at least write down what you're finding, that you're finding the derivative of velocity, which is acceleration. And then part C is the part that has the most work associated with it, although it's interesting as you go through part C, there's actually more than one acceptable answer. So what part C is saying is that at 10 hours, the train returns from where it started. So essentially what's happening is for the first 5 hours, we were traveling one direction. We had a positive velocity. And then from 5 to 10 hours, we notice in this chart, we actually have a negative velocity. So we're just going in reverse. And the idea is I want to cover the same amount of ground going forward as I do coming backward. And to do that, we want to figure out what could K possibly be to get this to happen. There are a couple ways to do this problem. First thing I wrote down is I want to look at the integral from 5 to 10 of v of t. And I want it to be the opposite of what I got in part A. So in part A, I got 166.667, and it's saying you can round to your nearest whole number. So if you want at that point to say I went 167 miles, so from 5 to 10, I need to get negative 167. I basically want to go in the opposite direction when I integrate it. I want to be going, whatever I went forward, I want to get the exact same going backwards. And then I'm going to do this either with a right Riemann or a left Riemann. And when I first looked at this problem, I thought, well, how do I know which one I want to do? They didn't give me any real idea. And then when you look at the solution manual, it says it doesn't matter. It does not matter. They would accept either one. There is a definite answer that you can do if you want to do a left Riemann. There's a definite answer you can get when you do a right Riemann. They are approximations, so you're basically either one would be acceptable. So I started this problem and I did a right Riemann. I guess I looked at the table and thought, well, I don't really want to use 0. Maybe 0 will throw it off. So I'm going to use a right Riemann. And when I do my right Riemann, what I see is that each of my widths are 1, so I don't even need to write that. And then I use negative 25, negative 20, negative 50, k, and negative 20. I added them all together, and I got negative 115 plus k equals negative 167. Then I added 115 to both sides, and I got negative 52. My pen's acting strange. Negative 52 is one approximation for k. And again, they said round to the nearest whole number, which is why from the start I wasn't using 167.6 repeating. I started, or 166.6 repeating. I started using 167. So that is one appropriate use of k for that approximation. They also said that you could use the left Riemann. So if you use the left Riemann, what it would look like is you still have the negative 167, and you still have the 1, but then it would be 0 plus negative 25 plus negative 20 plus negative 50 plus k. And when you do this, you get negative 167 equals negative 95 plus k. And you add 95 to both sides, you get k. Could be approximately 72. And it would be negative. Or negative 52. So you're looking at these two different values of k. And since they didn't give you more guidance for this problem and tell you what type of Riemann, I mean, I guess you actually could have done a trapezoidal or understand that the trapezoidal would have been the average, so that if you did the trapezoidal, your k value would be at negative 62. So you could even go that far, although they didn't mention it in the solution manual. But it shows you that both Riemann approximations give you an ability to do just that, to make an approximation. So this problem was kind of interesting because it was a little generic, which is something that we need practice with. It was a little bit with a table and the Riemann, but it also has a little bit with an equation where you're actually looking at the integral and the derivative of it. So a lot of things happening. You should see, you really should not spend a ton of time on this problem. There isn't one part that is very labor intensive, but it does allow you to review a lot of things in a pretty short period of time.